Welcome to the Deep Dive, the only place that transforms stacks of sources into essential, usable knowledge. Today, we are undertaking a deep dive into the very foundation of modern technology, the computer chip itself. And we're focusing on a silent crisis, really, that is fundamentally redefining how these chips are designed, manufactured, and timed. It's this huge shift from a world of predictable, deterministic certainty to a messy, statistical reality in nanometer circuits.
It's an internal revolution in silicon,
Yeah.
and the stakes could not be higher. For the past 50 years, we treated manufacturing like a precise machine,
Yeah.
where a circuit built the same way twice performed identically,
As it should.
as it should. But as we transition into feature sizes measured in just tens of nanometers, the performance of supposedly identical devices varies wildly. So our mission today is to analyze the sources that explain why these fluctuations, known as process variations or PV, why they are no longer a niche issue for specialized components. They are now the single primary limiter of yield, performance, and overall profitability for all digital circuits.
And what we found in our sources reveals this core paradox driving the entire dilemma. We aggressively chase continuous technology scaling because, well, it drives complexity and phenomenal speed. But that relentless scaling simultaneously introduces this crippling atomic level variability. I mean, we are talking about physical feature sizes now comparable to just a few hundred atoms, which means statistical chaos, not engineering certainty, governs performance. Okay, let's unpack this. Before all this statistical modeling became mandatory, the industry relied on an old methodology called corner analysis. It was the standard for decades. So, why did the chip industry stick with that method for so long, and why is it finally breaking down now?
Well, corner design was the standard because it was simple and it guaranteed success, but at a cost. It verified circuit performance at these extreme points, the corners of the process, voltage and temperature or PVT spectrum. Think slow, slow or SS and fast, fast, FF. The philosophy was simple, really.
And if it works at the absolute worst, it'll work everywhere else.
Exactly. It's an ironclad guarantee, which is why they loved it. But the catch, as you said, is the cost of that guarantee. See, the quarter design model assumed that all critical parameters, like channel length, oxide thickness, threshold voltage, all of them, pessimistically, hit their worst case extremes
Simultaneously, on the same chip.
simultaneously. And that was acceptable when chips were large and global variations, wafer to wafer differences were the main problem. But now, with nanometer scaling, the gap between the fastest and slowest corners has just grown geometrically.
So, if that corner gap is growing, the required guard band to ensure your calming works, that also has to grow.
It has to. And the core technical issue is the overwhelming impact of local corner. That is, intra-die variations relative to the global ones. Corner models are just terrible at accounting for these local differences.
Yeah.
The randomness within the chip, it makes the assumed worst-case scenario, that SS corner, a statistical phantom. It's a hypothetical failure point that rarely, if ever, actually occurs.
So, what does this over pessimism mean in dollars and cents for chip manufacturing? Because the consequence of relying on this old assumption is it's massive, costly guard banding and significant over-design. You are literally wasting silicon just to meet the timing targets of an impossible corner case.
The waste is staggering. Our sources gave a perfect case study, comparing corner design to a statistical design approach on a simple 10 inverter chain. The goal was to reliably meet a target delay of 661 picoseconds.
Okay.
A statistical design, one that aims for a reliable, say, mu plus 3 sigma target, so a 99.7% confidence level, that required increasing the gain size by 1.3x, a pretty reasonable guard band.
Okay, 1.3x sizing, that's an understandable safety margin. What did the old corner design require?
The SS corner design required 2.0x sizing to guarantee that unlikely worst-case performance. Now think about that difference. That single, overly pessimistic decision resulted in a 62.5% larger area overhead.
62.5%.
62.5%, and 44% higher power consumption than was necessary.
That's more than half of the silicon area dedicated to chasing a statistical ghost. That translates directly into fewer chips per wafer, lower yield, and, frankly, a competitive disaster.
Yeah.
Statistical design isn't just about modeling. It's about recovering massive amounts of wasted silicon and power. This shift is really about acknowledging reality. So before we talk statistical solutions, we need the language of the problem. What are the physical sources of this randomness that we now need to model so precisely?
Right. We classify process variations by how they behave. You have systematic variations, which are predictable, like those caused by the specific pattern layout or light diffraction and lithography. We can model and compensate for those pretty easily.
Those are the known unknowns.
Exactly. The challenge comes from non-systematic or random variations. We break these down further. There's inter-die or global variations that affect the entire chip equally, maybe due to temperature gradients across the wafer. But the truly disruptive force is intra-die local variation, which means two identical adjacent transistors on the same chip will perform differently. This local randomness is what killed corner design.
Let's get granular. What specific physical phenomena are responsible for this local randomness in, say, traditional planar transistors? Give us the two main culprits that designers focus on.
Okay. First, we have random dopant fluctuation, or RDF.
Wow.
In the transistor channel, performance depends on the concentration of these dopant atoms. When the channel area shrinks, the random placement and number of those atoms becomes statistically significant, causing this pure, uncorrelated randomness, primarily in the threshold voltage, VEEF.
So RDF is like rolling tiny physical dice for every single transistor on the chip.
That's a perfect analogy. The second major culprit is line edge roughness, or LER. Lithography doesn't print perfectly smooth polysilicon gate edges. They're rough. This random roughness causes variation in the channel length L. And crucially, LER is spatially correlated. This means that if the gate edge is rough in one spot, it's likely to be rough in the nearby spots too.
And here's where we move from physics to math. If delay is a function of these multiple random inputs, VEEF from RDF, L from LER, how do engineers actually combine that chaos and predict the total variance of the gate delay?
We model all these input parameters as random variables. To find the total gate delay variance sigma squared of D, we use a powerful approximation called a first-order Taylor series expansion. Conceptually, what this formula does, it analyzes how much the final delay will change for a small change in each input parameter, and then it adds those weighted contributions together.
Okay, so we're not just summing up the random errors, we're scaling them. What determines the weight given to each random input?
Well, the total delay variance is determined by summing the contribution at each process parameter, scaled by two factors. The first one is obvious. The parameter's own inherent variability, its own sigma squared. If LER is inherently very noisy, it contributes a lot.
Right.
The second factor is the square of the gate's delay sensitivity, and this is the critical design insight. Think of sensitivity as how much the gate delay flinches when a process parameter changes slightly. If a gate design is hypersensitive to variations in channel length, even tiny LER fluctuations can wreck its timing. The key insight for the design engineer is to find the parameter with the highest product of sensitivity squared and variance. That is the dominant factor they have to mitigate.
Let's follow that chaos down the line. We've been discussing a single gate. Now let's look at an entire logic path where the delay chain reaction might run through hundreds of gates. You mentioned spatial correlation earlier, the LER effect being patchy, not purely random. Why is that specific type of correlated variation the biggest danger for the timing of a long, critical path?
If we connect this to the bigger picture, the total path delay variance isn't just the simple sum of individual gate variances. We have to include the covariance term in our calculation.
And what exactly does that covariance term represent in the physical world?
It captures the impact of that spatial correlation. If two physically adjacent gates are connected in a timing path, and they are both affected similarly by a correlated parameter, the covariance term is high. It's non-zero only for spatially correlated parameters like LER, where the correlation factor, LER, is close to 1. And the covariance will be exceptionally high if those two gates are close and both are highly sensitive to that same variation source.
Let's use an analogy to clarify this crucial distinction between purely random effects like RDF and these spatially correlated effects like LER, especially over long distances.
That's essential. So imagine the path is a 100-meter sprint. Pure random effects, like RDF, are like the 100 runners having tiny independent random fluctuations in their starting reaction time. Some jump too fast, some too slow. Over a long path of many independent events, the law of large numbers kicks in.
Right, they start to cancel each other out.
They tend to cancel out. Our sources show the overall path variability for RDF decreases proportionally to 1 over the square root of n, where n is the logic depth. They essentially smooth out the path delay.
So random chaos actually helps you over long paths because the errors average away.
Exactly. But now consider fully correlated variations caused by LER. This isn't random noise. This is like a subtle systemic slant to the entire running track. If the first gate in the path is delayed because of LER, every adjacent gate is delayed by that same mechanism. This systemic error does not decrease as the path length increases. It just accumulates. That is why correlated variations, those caused by LER that affect Multiple, physically close, high sensitivity gates are the dominant concern for long critical logic paths. You cannot average away a systemic bias.
Which means we can't just wait for the randomness to cancel out. So if we embrace the statistical reality and our models tell us exactly where the sensitivity hotspots are, what are the practical design levers we can actually pull to control this variability on the silicon?
The statistical models immediately reveal the four most powerful levers that influence the standard deviation of gate delay, or sigma d. The first and most effective is simple: sizing a logic gate. We found that increasing the transistor width the W directly and significantly reduces the gate's delay sensitivities to these process parameters. So by identifying high sensitivity gates and just making them slightly wider, we are using silicon area strategically to drop the sigma d where it matters most.
So we're not using the 2.0x guard band everywhere like the old corner design, but selectively sizing up only the most sensitive components.
Smart. Precisely. We focus our spending. The second lever relates to the surrounding circuit, load capacitance. Nodes that have a high fan-out or long interconnects, long wire routing, they have naturally high delay sensitivities. They are major sources of timing variation, and the logic gates driving them must be prioritized for these sizing adjustments.
And the third lever represents what sounds like the biggest trade-off in modern low-power design.
That's the power supply voltage, or VDD. Reducing VDD dramatically increases the statistical variation in performance. If a design operates too close to the transistor's threshold voltage, small random changes in VETH, due to RDF, have a disproportionately large impact on switching speed. Designers pursuing aggressive low-power strategies must be acutely aware that lowering voltage drastically amplifies timing uncertainty.
And speaking of scaling limits, planar transistors eventually hit a physical wall, which forced the industry to fundamentally change the structure. Around the 22 nanometer node, we shifted to 3D FinFETs. So we tried to fix the design, then we just fixed the transistor structure itself.
Yet that structural change was mandatory. FinFETs offer superior electrostatic control over the channel, which initially helped reduce some variability. However, they introduce entirely new enemies. For instance, the multicrystalline nature of the metal gate means work function variation, or WFV, stemming from random grain orientations. That becomes the new dominant pure random effect, effectively replacing RDF.
And how does that new structure, where the device is built using multiple fins or parallel channels, how does that change the statistical math we just discussed?
It changes radically, especially for multi-fin devices. We use more fins to increase current drive, but the statistical rules are different. For the pure random effects like WFE, the law of large numbers still works beautifully. If you have 4 fins, the random variability averages out across those 4 fins, and the variance scales linearly with the number of fins n fin.
Okay, that's good.
But here is the critical problem. The global or correlated variations, the ones we can't average out, they affect all fins simultaneously because they share the same spatial correlation. This means that instead of a linear increase in variance, we see a much stronger quadratic increase in variance n fin squared relative to the number of fins. This makes correlated effects even more terrifyingly difficult to manage in these advanced 3D structures.
Let's end this section with the highest stakes example memory. SRAM cells are replicated billions of times on a chip. Failure is unacceptable. You need guaranteed reliability beyond the standard 3 sigma.
Absolutely. This is where high sigma analysis becomes mandatory. We need confidence levels, often approaching 6 sigma, or 1 failure in a billion. Process variations significantly shrink the static noise margin, or S&M, a key indicator of how reliably the memory cell can hold its data against noise. The problem is doubly bad at low supply voltages used for power saving. Low VDD shrinks the margin, and process variation smears the performance, pushing billions of cells closer and closer to catastrophic failure.
This deep dive shows that designing chips today it's less like deterministic architecture and more like advanced statistical risk management. We are moving from engineering based on certainty to engineering based on probability. We've seen the core principles needed for success. You have to model variation accurately, paying critical attention to those spatially correlated effects that accumulate. And you must design with sensitivity in mind, using selective gate sizing and voltage scaling as explicit data-driven levers.
And crucially, you must quantify the economic advantage. By embracing statistical resilience, designers avoid that massive 62.5% area overhead imposed by the overly pessimistic corner methods. That directly translates technical insight into profitability. This transition isn't just a tweak, it is a fundamental paradigm shift away from simply guarding against worst-case hypotheticals and towards designing circuits that are statistically resilient from the atomic level up.
Which leaves us with a final provocative thought for you to consider. Given that reducing the power supply voltage dramatically exacerbates the impact of statistical variation, shrinking noise margins, and amplifying uncertainty, how might the industry truly balance the relentless competitive drive for power efficiency against the fundamental physical limits of reliability without sacrificing yield? That is the trade off currently being negotiated in every single advanced chip design. Thank you for joining us for the deep dive. We'll see you next time.